In this video, I want to talk about the differences between initial value problems and boundary value problems, and sort of conceptually discuss why you have to use different mathematical approaches to solve them. And I'm going to use heat exchangers to illustrate these concepts. So I'm a chemical engineering professor. Heat exchangers are like comfort food for chemical engineers, perhaps also mechanical engineers, but I don't know that for a fact. A heat exchanger is a unit in which I flow two fluids through some chambers, for example, maybe a shell and a tube, and the fluids are allowed to exchange energy through heat transfer. So you might be using cooling water to cool down a fluid that comes out of a reactor or something. And I'm not going to draw the piping system in too much detail, but I'm just going to schematically just draw two fluids flowing through a channel. The dotted line or the dashed line refers to a barrier. The fluids don't mix, but they're allowed to exchange heat. And there's another video in my YouTube channel that actually goes through the setup of the differential equations. This time, I'm just going to tell you what the differential equations are. We'll discuss intuitively why they make sense, or at least why they seem to make sense. These alphas are constants. They depend on fluid properties such as density and heat capacity, and also flow rate, which would affect the heat transfer coefficient. But I don't want to focus on the engineering aspect of this problem. I just want to talk about the mathematical aspects using a semi-physical intuition. Normally, in a problem like this, we would know the temperatures of the fluids that we're actually sending into our process. So we would know T1 of 0, T2 of 0. I'm just going to give them numbers just so that it's clear that we know them, not that these numbers mean much. So let's think a little bit about what is happening here. So if I know, well, let's first think physically. So if I know the temperature of stream 2 here and stream 1 here, and intuitively, we ought to know that the energy transferred from one stream to another should depend on the difference in temperature, right? Heat flows from hot to cold. In this case, stream 1 is warmer than stream 2, so there should be an exchange of energy in this direction. And quantifying how that exchange of energy affects temperature is effectively what we did when we derived these differential equations. So if I know T1, I know T2, I could calculate the energy transfer. Then you might imagine that I could evaluate or estimate the temperature at some step delta x away, right? Stream 2 is going to be heated up by a little bit of heat transfer from stream 1. Stream 1 will be cooled down because it exchanged heat to stream 2. Looking at it mathematically, if I know at x equals 0, T1 is 80, T2 is 25, I can calculate everything that's on the right-hand side of this equation, right? And I can then get the derivatives. And if you know a number and you know the derivative with respect to x, you can estimate what it's going to be at some step delta x. So for example, T1 at 0 plus delta x would equal T1 at 0, actually, it wouldn't equal that. It would be approximately equal that, plus dt1 dx times delta x. I could do the same thing for stream 2. So if I could calculate the derivatives and the temperature, I can estimate the temperature at some step delta x away. So that's how you solve this differential equation. So to calculate the solutions, we start at known temperatures, and then we calculate derivatives, and then we step forward by a little delta x, and we recalculate the temperatures. Those new temperatures that you evaluated delta x can then be fed back into that system of differential equations to get a new estimate for the derivatives, and then we can continue to march forward. So it may require a computer to do many steps, but we can get an answer. This is, by the way, known as a co-current heat exchanger. Co-current just means that the fluids are both traveling in the same direction through the heat exchanger. So now let's look at another possibility. This is a countercurrent heat exchanger. So now imagine stream 2 is flowing from left to right, but stream 1 is now going the other direction. At x equals 0, I know T2. And I'll use the same value. Let's call it 25. And remember how I said that normally an engineer would know the fluid temperature entering a system? Well, the other stream, T1, is entering the system on the other side. So I have the same amount of information here in the sense that I know temperature 2 at one position, I know temperature 1 at one position, which is the same amount of knowledge, or at least a similar amount of knowledge as in the co-current situation. But notice that there is a big difference here. So by the way, this is countercurrent. So with a countercurrent heat exchanger, I don't know the temperatures at the same position, right? Because my boundary conditions, my known boundary conditions occur at different values of x, this is known as a boundary value problem. So if you try to talk through the methodology we discussed for the co-current heat exchanger, you'll see that that same type of thinking doesn't work very well for a countercurrent heat exchanger. So for example, if I wanted to estimate T2 at some value delta x, right? So if I know T2 at x equals 0, if I knew T2 prime at 0, then I could estimate T2 at 0 plus delta x. By the way, the differential equation for this boundary, or for the countercurrent heat exchanger, looks very similar. I'm sorry, I forgot to write that down. I should have done that first. It looks very similar to the differential equation that we saw for the co-current case. So if you come back here, the stream 2 has not changed. This differential equation should match this one. But it turns out that if you go through the derivation, because we switched the flow direction of stream 1, we added a negative sign to the differential equation in terms of T1. Very similar form though, right? So coming back here, if I wanted to calculate T2 at x plus delta x, or 0 plus delta x, I would need to know dt2 dx. Now here, hopefully you can see a problem here, because that derivative, dt2 dx, depends not only on t2 at x equals 0, which we know, but it also depends on t1 at x equals 0. And that should make sense, because the temperature change locally to T2 is going to depend on the heat transfer that occurs between stream 1 and stream 2. So we need the stream 1 temperature at x equals 0, and we don't have it. You can do another or very similar type of thinking on the other side. So as stream 1 enters here at x equals L, we do know the stream 1 temperature, but we don't know the stream 2 temperature. So again, we cannot see how stream 1's temperature is going to change using the type of reasoning we applied to the co-current heat exchanger. I'm not saying that this problem can't be solved, but I am saying that you need to think about it differently. And that's all I'm going to say in this video, because my purpose was just to illustrate that there's a difference in the situation. So one more word of summary. This is an initial value problem because we know the boundary conditions at the same position of x. In this particular case, x equals 0, but it could have been any other position of x. As long as we have boundary conditions at the same value of x, it's an initial value problem. This is a boundary value problem because even though I have the same number and very similar looking boundary conditions, I don't have them at the same position of x.